In the winter of 2019, something changed in the night sky that required no telescope, no equipment, no degree in astrophysics to notice. Orion's right shoulder, one of the most recognizable points of light in the entire winter sky, burning red-orange for every civilization that has ever looked up, got noticeably dimmer. Not all at once, not dramatically, but undeniably. People who had never consciously tracked the brightness of a single star looked up at Orion and felt that something was off. Today, we follow that dimming to its source. What we found there doesn't just explain one strange winter. It changes what we thought we understood about how stars lose mass, how they age, and what they're capable of doing when no one is watching closely. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Betelgeuse ejected a chunk of itself the size of several planets combined. Imagine watching a familiar face for years, noting its light, its color, its faint variations with the seasons, and then, over the course of a few weeks, noticing that part of it had grown dimmer. Not sick, not changed in any way you could name precisely, just less. And then learning months later that what had actually happened was that this person had cast a piece of their own skin into the air as a cloud, that the cloud had drifted between you, that it was absorbing the light that would otherwise have reached you. That is roughly what Betelgeuse did. In the autumn of 2019, Betelgeuse, a red supergiant star burning roughly 700 light-years from Earth, one of the dozen or so brightest objects in the entire night sky, began to dim. Not subtly. By February 2020, it had faded to its lowest measured brightness in recorded history. Over a century and a half of systematic observation, no one had seen it this faint. Astronomers around the world turned instruments toward it. Amateurs tracked it nightly. Papers were published. Debates erupted. Was it about to explode? Was it something on the surface? Was it dust? Was it something nobody had categorized yet? The answer, when it came, was more unsettling than any of the theories that preceded it. Betelgeuse had erupted. Not in the explosive, cataclysmic supernova sense, but in a way that had no real precedent in stellar physics as it had been formalized up to that point. A convective cell on its surface, a bubble of superheated plasma, enormous beyond comfortable comparison, had risen, broken through the photosphere, and launched a mass of material equivalent to several times the mass of Jupiter into the surrounding space. Not slowly, the way stellar winds move, in a single convulsive event spanning weeks. That material cooled as it expanded outward. It condensed into dust, and the dust hung between us and the star, blocking a substantial portion of its light from ever reaching Earth. We had watched in something close to real time, a star sneeze away a piece of itself. Not through the slow, patient stellar wind that models had always described as the primary channel of red supergiant mass loss. In an event without an existing name, researchers coined one, surface mass ejection, a category of stellar behavior that hadn't been accounted for in the equations that predict how stars like this evolve, how much mass they carry to their deaths, and what those deaths leave behind. This was not the story of one anomalous winter. It was a crack in something much larger. The models describing how red supergiants shed mass over their lifetimes, the models used to calculate how much material these stars contribute to the interstellar medium, what kind of supernovae they produce, what remnants they leave. had been built without accounting for events like this. If Betelgeuse can do this, the question that follows is quiet but persistent. Which other red supergiants have done it already, are doing it now, in parts of the galaxy where no monitoring program exists? We'll spend the next several hours with this star, with what it is, what it did, and what the doing reveals. Betelgeuse is still out there, still burning, still variable, still slowly preparing, in its own geological sense of the word, for a death that will eventually be visible from Earth in daylight. But we start with the dimming, with what it took to find the answer, and with why that answer changes the way we look at every other red star in the sky. A star that lives at a different speed. Betelgeuse is a red supergiant, and that classification tells you something immediately about how it arrived at its current state. A red supergiant begins its life as a massive, hot, blue-white star. Massive means, in this context, somewhere between 10 and 20 times the mass of the Sun. This matters because stellar mass governs everything. The rate at which nuclear fuel is consumed, the internal pressure, the temperature, the lifetime, the mode of death. A star with 10 to 20 solar masses burns its hydrogen supply at a rate that would be incomprehensible scaled against the Sun's consumption. The Sun has been fusing hydrogen in its core for about 4.5 billion years and is roughly halfway through its supply. Betelgeuse burned through its entire core hydrogen stock in approximately 8 to 10 million years. Before the first land animals evolved on Earth, before the Great Permian extinction, before the asteroid that ended the Cretaceous era, Betelgeuse had already finished the phase of its life that the Sun is still living. When a massive star exhausts its core hydrogen, gravity temporarily wins. The core contracts and heats. Hydrogen fusion shifts to a shell surrounding the core, and a new, hotter reaction begins in the core itself: helium fusion. The outer layers of the star respond to the changed internal pressure distribution by expanding enormously. The total luminosity stays roughly similar, but this energy is now distributed over a vastly larger surface area. Temperature drops. Color shifts from blue-white toward orange and red. This is how Betelgeuse became what it is now. An ancient, expanded, cooling object with a dim surface and an interior still burning through progressively heavier elements in layered shells. Its diameter is uncertain, and that uncertainty is itself a piece of information. Betelgeuse is one of the very few stars in the sky that can be imaged as a resolved disk rather than a point source, because it is close and large enough for the largest telescopes to discern its actual face. But the photosphere, the layer from which most light is emitted, grades off into an extended, turbulent, asymmetric atmosphere that makes surface partly a matter of definition. Current best estimates place Betelgeuse at roughly 700 to 900 times the diameter of the Sun. Even at the low end of that range, if placed at the center of our solar system, it would engulf the orbits of Mercury, Venus, Earth, and Mars, and push deep into the asteroid belt. Its mass has been harder to pin down precisely. The initial mass was likely between 15 and 20 solar masses, but Betelgeuse has been losing mass through stellar winds for millions of years, and now, we know, through at least one massive surface ejection. Current estimates for its remaining mass fall between roughly 10 and 20 solar masses, with the uncertainty again being informative. We don't fully know how much mass it has shed. Its surface temperature is approximately 3,500 Kelvin. The Sun burns at about 5,800. Rigel, the blue-white star at Orion's foot, burns at something close to 12,000. The color difference is real and visible to the naked eye. Betelgeuse's red-orange glow is a direct expression of its cooler surface. It pulsates. On a roughly 400-day cycle, the outer layers oscillate, expanding outward, cooling and dimming, then contracting, reheating, brightening. There is also a longer oscillation, near 5 to 6 years, and a third, less clearly defined variation on a timescale of decades. These are not perfectly regular. The star is not a metronome. It is more like a very large animal breathing unevenly across different timescales simultaneously. And it will die in a supernova. This is certain. Only the timing is unknown. The name carries 7 centuries of mistranslation. The name Betelgeuse has a complicated history, and the complication is worth pausing on, because it tells something true about how knowledge accumulates. The star was known to medieval Arab astronomers as Yad al-Jawza, meaning roughly the hand of Orion. Al-Jawza was the Arabic name for the constellation, and the star marked one of the figure's limbs. When this name traveled into European astronomical texts through Latin translation in the 12th century, something went wrong. The initial letter, a Y sound in Arabic that appears visually like a B in some manuscript traditions, was misread. The name entered Latin as Betelgeuse, then as Betelgeuse, then through a series of further corruptions and reprinting errors into the form we recognize today. Betelgeuse, in its final form, doesn't mean anything coherent in any language. It is a phonetic fossil, a fragment of Arabic stripped of its meaning over 6 centuries of successive mistranslation, arriving in the modern era wearing a name that sounds invented but carries, if you listen carefully, the ghost of an Arabic phrase about a hand. This history matters more than it seems. Arab astronomers had been systematically tracking Betelgeuse since at least the 9th century. Abd al-Rahman al-Sufi, a Persian astronomer working in the 10th century, documented it in his landmark star catalogue of 964 CE, noting its color among the brightest red stars in the sky. Long before systematic astronomy, Babylonian sky watchers had their own names and associations for the stars of Orion. The ancient Egyptians linked the constellation to Osiris. Cultures in the Pacific used the configuration for navigation. Every civilization that developed in the northern hemisphere and looked up at the winter sky eventually noticed the same loose grouping, the belt, the shoulders, the feet, and built its own story around it. Betelgeuse was always there, reliably orange-red, reliably bright, reliably positioned at the upper left portion of the figure regardless of which figure was being drawn. There is something worth pausing over in that continuity. The light we see from Betelgeuse left the star roughly 700 years ago. The people in Baghdad, in Samarkand, in medieval European observatories, who named and renamed and named it again, were receiving light that had been traveling for 600 or 700 years before them. The light arriving tonight left the star around the year 1325. In 1325, the star was already ancient, already in the later phase of its red supergiant life, already shedding mass, already pulsating on its long, irregular cycles. None of that was knowable then. The light arrived at their eyes and they gave it a name. The name broke in translation, and we've been using the broken version ever since. Standing inside it. Start with a specific point. The Sun's diameter is about 1.4 million kilometers, This is large enough that if the Sun were hollow, you could fit roughly 1.3 million Earths inside it. The distance from Earth to the Sun, one astronomical unit, the basic measuring stick of the inner solar system, is about 150 million kilometers. Take Betelgeuse at a conservative estimate of 800 times the Sun's diameter. That places its photosphere at roughly 1.1 billion kilometers from its center. Earth's orbital diameter, the full width of Earth's path around the Sun, is about 300 million kilometers. Betelgeuse would encompass that orbit entirely, with enormous room left over. Mars orbits at a mean distance of about 230 million kilometers from the Sun, which gives it an orbital diameter of 460 million kilometers. Still inside Betelgeuse. The asteroid belt occupying the gap between Mars and Jupiter begins at about 330 million kilometers from the Sun, also inside. Jupiter, the largest planet in the solar system, orbits at a mean distance of about 780 million kilometers. The photosphere of Betelgeuse, on the conservative estimate, reaches just past that distance. If you replaced the Sun with Betelgeuse, you would be standing inside the star, not orbiting it, not near its surface, embedded in its outer atmospheric layers, material so diffuse at that radius that it barely registers as plasma by laboratory vacuum standards, but still glowing, still at thousands of Kelvin, still hot enough to destroy any known material instantly. From inside Betelgeuse at the position of Earth's orbit, the star would not look like the Sun looks. There would be no defined disk, no clean edge to shield your eyes from. The glow would surround you in every direction, a vast, dim, orange-tinted luminescence emanating from all of space around you. Not blindingly bright, the surface is cool by stellar standards, but present everywhere. This is the object that appears in our sky as a slightly orange point, about the same apparent size as a planet seen without a telescope, slightly brighter than most other stars in Orion. Astronomical distances compress things in ways that intuition never quite catches up to. The boiling surface, no one expected to see. In 1996, the Hubble Space Telescope produced an image that had never been produced before. Not because Betelgeuse was at the top of any particular priority list. The observation was possible because Betelgeuse is close enough and large enough that Hubble could do something it cannot do for any other star in the sky except the Sun. Resolve the disk. Produce an actual image of the star's face, not just a point. And what the image showed was not what people had assumed they would find. The surface of Betelgeuse was not uniform. It was not a smooth, featureless sphere emitting light evenly from all directions. It had a large, bright region in one area of the disk, a region significantly hotter and brighter than its surroundings. The surface was asymmetric, lumpy, structured. Subsequent observations over the following decades expanded this picture. The asymmetry was real and variable, shifting over months and years as the surface evolved. Betelgeuse has convection, as stars generally do, the process by which hot material rises to the surface, cools, and sinks back down. But the scale of convection in Betelgeuse bears no resemblance to the scale of convection in the Sun or in any terrestrial context. The Sun's granulation, the individual convection cells visible on its surface, is roughly 1,000 kilometers across. Supergranules can reach 30,000 kilometers. These are large in absolute terms, but they are small compared to the Sun's 1.4 million kilometer diameter. Betelgeuse's convection cells are estimated, from observations and from modeling, to span something like a quarter of the star's radius. A convection cell on Betelgeuse is a rising column of plasma, roughly the distance from the Sun to Jupiter in width. Individual bubbles of superheated material, drifting upward over months, cooling at the surface over more months, sinking back over years. The surface of Betelgeuse, if you could observe it at human resolution, would look like a slowly boiling sea. But with each individual bubble the size of a small country or a large continent, moving on timescales of seasons rather than seconds. This was the first image of the surface of any star other than the Sun. It stopped being a point of light that night and became a place. A century and a half of patience. Systematic photometric monitoring of Betelgeuse, careful, calibrated measurements of its brightness, conducted consistently over time, goes back to roughly the mid-19th century. The American Association of Variable Star Observers, founded in 1911, has accumulated brightness records stretching over 150 years. This is an extraordinary archive by any measure. It consists of hundreds of thousands of individual measurements, many made by amateur astronomers with modest equipment, contributed over generations to a collective database that no single professional observatory could have built on its own. Within this dataset, the 400-day pulsation cycle is clearly visible. Betelgeuse brightens and dims on that cadence with moderate regularity, rising from minimum to maximum by roughly a full visual magnitude in favorable cycles, then declining back over the following months. Below that oscillation, the longer multi-year cycle, approximately 5 to 6 years, rides as a slower modulation of the baseline brightness. A third, decadal variation is suspected but less cleanly characterized. The historical record contains anomalies. Some epochs in the early 20th century show unusually deep minima. Some periods show unusually rapid brightening. The star is not perfectly periodic. Researchers who have studied the AAVSO light curve describe it as semi-regular. Genuine periodicities are present, but they drift. The amplitude varies, the timing shifts. In this context, the 2019 to 2020 dimming can be placed precisely. Before it, the deepest minimum in the full observational record was around 1927, a value near magnitude 1.4, commented upon in observational reports of that era and later identified as an outlier in retrospective analyses. The Great Dimming reached approximately 1.64, faint enough to be the most extreme measured value in over 150 years of continuous documentation. There is one additional piece of context that matters for interpreting the timing. The Great Dimming occurred near the simultaneous minimum of both the 400-day cycle and the longer multi-year cycle. These two periodicities were aligned, heading toward their respective troughs at approximately the same time. This coincidence would independently produce a somewhat deeper than average minimum. It was not the cause of the Great Dimming. The scale was far too extreme for the pulsation alone to explain. But it deepened the dimming and extended its duration in a way that made the combined event appear even more dramatic. The 150-year baseline is what made 2019 legible as genuinely anomalous. Without it, the dimming would have been puzzling but ambiguous. With it, the magnitude of the deviation from baseline behavior was unambiguous. That archive was built by people who mostly never met each other across several generations, using instruments ranging from the naked eye to backyard telescopes to professional-grade photometers. Each measurement was a small thing. Together they built the only tool capable of recognizing what was happening. The man who had been watching for 40 years. Edward Guinan had been paying close attention to Betelgeuse since the late 1970s. He is an astronomer at Villanova University in Pennsylvania, and Betelgeuse has been among the stars he monitors most carefully across his career. His longtime collaborator Richard Wassertonic, also at Villanova, has contributed thousands of individual brightness measurements to the monitoring record over the same period. A sustained observational commitment that is somewhat unusual in professional astronomy, where funding and instrumentation priorities tend to shift over timescales of years rather than decades. By October 2019, both Guinan and Wassertonic had noted something. Betelgeuse was fading more quickly than the 400-day cycles approaching minimum would account for on its own. The slope of the decline was steeper. The departure from the expected trajectory was small but real. Guinan posted a notice to the Astronomers Telegram, a rapid communication platform used by professional astronomers to flag time-sensitive observations to the community, in December 2019. The message was technically careful, grounded entirely in the photometric data. But the implication was legible to anyone reading between the lines. Something different was happening, and the wider community should be watching. Within days it was. Professional observatories began directing observing time toward Betelgeuse. Space-based missions cued observations. Researchers with access to ultraviolet and infrared instruments, wavelengths that can probe the circumstellar environment and the upper stellar atmosphere in ways that ground-based visible light telescopes cannot, began requesting data. And the amateur community mobilized. Variable star observers who already contributed regularly to AAVSO increased their observing cadence. Astronomers who hadn't submitted a Betelgeuse measurement in months began submitting nightly. There are accounts from this period of hobbyist astronomers, people with small backyard telescopes and decades of experience watching variable stars, who recognized from their own data independently that this fading was not normal. What Guinan and Wassertonic had caught was not obvious. It required knowing the star's normal behavior well enough to recognize a departure from it. That knowledge takes years to accumulate. In this case, it took 40. The Great Dimming was announced to the public, by newspapers, by science journalists, by social media, as a sudden mystery. From the inside, it had been building since October, tracked by people who had been watching long enough to know what normal looked like. The question that was already in the room. It needs to be said plainly. When Betelgeuse dimmed in the winter of 2019, the immediate public interpretation, voiced in comment sections, in casual conversations, in the framing of many news articles, was that it might be about to go supernova. The interpretation was understandable. Betelgeuse is a massive star in the late stages of its life. It will die in a supernova. This is not in question, only the timing. It is one of the nearest massive stars to Earth, and it was behaving in a way that had never been recorded in over 150 years of careful observation. The professional astronomical community was significantly more cautious. Pre-supernova dimming was not expected to look like this, at least not according to existing models. The theoretical picture of what a massive star does in the hours, days, and weeks before core collapse involved a different kind of brightening and variability than what was observed in the winter of 2019. The timescales didn't match. But the question was legitimate in a deeper sense than its immediate answer deserved. Humanity has not observed a nearby supernova in the era of telescopic astronomy. The last supernova visible to the naked eye in the Milky Way, the one documented by Johannes Kepler and others across Europe and Asia, occurred in 1604. Every astronomer alive today, every professional and amateur who has contributed to the understanding of stellar physics over the past 4 centuries, has grown up expecting to miss this event. The next Milky Way supernova is expected, by average rates, to occur within the next few hundred years. But averages don't constrain individual events. It might happen in 50 years. It might happen in 500. The last large supernova close enough to study in real detail was SN 1987A in the Large Magellanic Cloud, about 168,000 light-years from Earth. Even at that distance, it delivered a burst of neutrinos detectable by 3 underground detectors and was briefly visible to the naked eye from the southern hemisphere. Betelgeuse is at 700 light-years. A supernova there would be an order of magnitude more spectacular and scientifically significant than SN 1987A. It would be visible in daylight. It would cast faint shadows at night. It would be written about in every language in the world. When Betelgeuse dimmed in 2019, the discomfort people felt was not irrational. If the models can be wrong about how a star dims, they might also be wrong about how much warning a supernova gives. The margin between not going supernova and we think it's not going supernova is not zero. It turned out not to be a supernova signal, but the question it raised about the reliability of our models was not dissolved by the answer. It just shifted form. What a supernova at 700 light-years actually means. Begin at the scale of the event itself. A core collapse supernova releases, in a matter of seconds, more energy than the Sun will produce across its entire 10 billion-year lifetime. The iron core collapses to nuclear density in less than a second. The outer layers, which had been burning and slowly expanding for millions of years, are suddenly driven outward by the shock wave from the core collapse at velocities reaching a significant fraction of the speed of light. The entire mass of the star's outer layers, everything above the core, is accelerated from roughly stationary to tens of thousands of kilometers per second in an interval that is short by any measure. From a safe distance, this is extraordinary. From 700 light-years, a distance that places Betelgeuse firmly within what astronomers would call the solar neighborhood, a supernova is spectacular but not physically threatening. The primary concerns would center on the burst of radiation, particularly ultraviolet and X-ray, which would be significantly more intense than sunlight in those wavelengths. From 700 light-years, this enhanced radiation would be detectable and measurable, perhaps comparable to a modest increase in the total UV dose reaching Earth's surface. But Earth's atmosphere handles such inputs without difficulty. No serious damage to terrestrial life. The neutrinos arrive first. They travel at effectively the speed of light and interact almost not at all with the matter they pass through. Of the extraordinary number of neutrinos produced in the core collapse, numbers that require the kind of notation we've agreed to avoid in narration, but the figure is genuinely enormous. Nearly all pass through Earth as if it weren't there. A measurable fraction, perhaps dozens of events, would be captured by large underground neutrino detectors. These detectors would register the Betelgeuse supernova hours before the visible light reaches its peak. Then the light arrives. Not all at once. The optical brightness rises over hours to days as the shockwave reaches and breaks through the stellar surface, and then continues rising as the expanding fireball cools through the visible band. For the peak weeks and months of a Betelgeuse supernova, Orion would be fundamentally different from the pattern that humans have been recognizing for at least 10,000 years. The right shoulder would blaze. In the weeks following the initial explosion, it would appear in daylight as a sharp white point, fainter than the sun but genuinely visible. At night, it would illuminate the ground faintly, cast soft shadows, be bright enough to interfere with dark sky observation of other objects. Then it would slowly fade. Over months, the fireball cools. Over years, the remnant disperses. Over centuries, what was once a bright point becomes a faint, expanding nebula, visible only through telescopes, but one of the most studied objects in astronomy. Orion would have a gap. The shape that people have been drawing and naming and navigating by for thousands of years would be missing its upper left star. The last time we watched a star die. On the morning of February 23rd, 1987, a Canadian astronomer named Ian Shelton was developing photographic plates at Las Campanas Observatory in Chile. He had been imaging the Large Magellanic Cloud, the small satellite galaxy orbiting the Milky Way, visible from southern latitudes as a soft smear in the sky. When he compared the plate from that night against a reference image, there was a bright new point of light that hadn't been there before. He walked outside, looked up. The point was visible to the naked eye. In the hours that followed, the community realized what had happened. A star in the Large Magellanic Cloud had undergone core collapse. The light from the event, having traveled for roughly 168,000 years before arriving at Earth, had reached detectable intensity in the night sky of February 23rd, 1987. Before Shelton noticed the optical brightening, underground neutrino detectors in Japan, the United States, and the Soviet Union had already captured a brief pulse of particles, a burst lasting approximately 12 seconds, representing the neutrino flood from the core collapse. This was the first detection of neutrinos from any astrophysical source beyond the Sun, and it was transformative for theoretical astrophysics. It confirmed directly the core collapse model. The vast majority of the energy in a supernova is released not as visible light, but as a flood of neutrinos that passes through the entire planet as if it were barely there. The star that died, designated Sandulik -69 degrees 202 in catalogues, known to the relatively small number of astronomers who had ever noted it, had been a blue supergiant. This was surprising. The theoretical expectation was that core collapse supernovae came from red supergiants. A blue progenitor forced a significant revision of the models describing which stars explode and in what state. Betelgeuse is a red supergiant. It is more classically positioned in the theoretical picture of a pre-supernova star. But SN 1987A's blue progenitor was a reminder that theoretical expectation and physical reality diverge in specific cases. The supernova remnant has been continuously observed ever since, an expanding ring of shocked material, lit by the collision of the outward-moving ejector with a ring of material that the star shed centuries before the explosion, has been one of the most actively studied objects in modern astrophysics. It grows visibly from year to year in Hubble images. It began with one person, alone at 3 in the morning, walking outside to check something that looked wrong on a photographic plate. 2 explanations, 2 predictions. By early 2020, the professional community had narrowed the competing explanations for the Great Dimming to 2 primary categories. The first, something had changed on the surface of Betelgeuse itself, a large cool region, a star spot or an asymmetric cooling of the photosphere, was reducing the amount of visible light emitted from that part of the disk. This is analogous to sunspots on the Sun, though the scales involved would be very different. On the Sun, sunspots, regions of strong magnetic field that suppress convective heat transport, cooling the local surface by about 2000 Kelvin, typically cover a tiny fraction of the total disk. On Betelgeuse, known to have enormous convective structures, a cool region covering a large fraction of the visible hemisphere was conceivable. The second, something was present between Betelgeuse and Earth, specifically a cloud of material recently ejected from the star's outer layers that had cooled and condensed into dust. This dust was intercepting light from the star before it reached our telescopes. These 2 explanations make different predictions, and several of those predictions could be tested. A surface cooling event would affect the star's spectrum by reducing the effective temperature. Cooler plasma emits relatively more red light and relatively less blue and ultraviolet. The stellar atmosphere above the photosphere, which generates ultraviolet emission, would cool somewhat in tandem. The ratio of ultraviolet to visible light might decrease, but not dramatically. An obscuring dust cloud would redden the light passing through it by a different mechanism. Dust preferentially scatters and absorbs short wavelengths over long wavelengths. This is a wavelength-dependent extinction, not a thermal effect. The resulting reddening has a different spectral shape than photospheric cooling. And critically, the ultraviolet emission from the stellar atmosphere above the photosphere might be affected independently, either reduced by the dust or potentially elevated if the ejection event had deposited energy into the upper atmosphere. Color measurements of Betelgeuse during the dimming showed real reddening, and the shape of that reddening was more consistent with dust extinction than with simple photospheric cooling. But the definitive evidence required Hubble. What Hubble saw in the ultraviolet. Andrea Dupree is an astronomer at the Harvard-Smithsonian Center for Astrophysics, who has been studying Betelgeuse for many years. When the dimming began in late 2019, she was among the researchers who recognized immediately that ultraviolet observations, the kind only a space telescope above the atmosphere can make, were the most direct path to distinguishing the competing explanations. She had been monitoring Betelgeuse with Hubble across multiple observing cycles. The data available to her extended back months before the public noticed anything unusual. When that data was analyzed, it showed something that preceded the optical dimming and pointed directly at its cause. In the months before Betelgeuse began dimming in visible light, starting in approximately late 2019 and into early 2019, a region of the photosphere had brightened significantly in ultraviolet emission. This brightening indicated an outward convective eruption, a massive bubble of plasma rising from deep within the star, carrying elevated thermal energy to the surface and pushing material outward from the photosphere into the circumstellar environment. Then, following that ultraviolet brightening, the same region dimmed dramatically. The ultraviolet flux dropped. The optical dimming followed. The sequence was definitive. A convective outflow pushed surface material outward into the space above and around the star. As it moved outward and away from the star's heat, it cooled. At temperatures of roughly 1,500 Kelvin, silicate dust grains condensed from the cooling gas. The resulting dust cloud, irregular, concentrated in the direction of the initial ejection, sat between Earth's line of sight and the star's southern hemisphere, absorbing a significant fraction of the light that would otherwise have reached our telescopes. Not a supernova precursor, not a star spot. A new category of event, observed for the first time in real time, named afterward a surface mass ejection. The surface mass ejection, a named thing that hadn't existed. The Sun produces coronal mass ejections, CMES. These are eruptions of plasma from the outer solar atmosphere. The corona, driven by the rapid release of magnetic energy when tangled magnetic field lines restructure themselves. A large CME can carry billions of tons of material into the solar system at speeds of several million kilometers per hour. When directed toward Earth, large CMEs can disturb the planetary magnetic field, produce vivid aurora at unusually low latitudes, and in the most extreme cases, disrupt satellite communications and electrical grid infrastructure. These are significant events, but they are small. The material ejected by Betelgeuse in the 2019 event is estimated at roughly several times the mass of Jupiter. One Jupiter mass is about 320 times the mass of Earth. The Betelgeuse ejection, even at the lower end of estimates, moved more mass in a matter of weeks than the Sun moves in CMEs over thousands of years. There is no direct analog for this in solar physics. The scales are so different that comparing the two events is almost more misleading than illuminating. The Sun and Betelgeuse are both stars, but they occupy different classes of stellar behavior in the same way that a canoe and an ocean freighter are both vessels. The mechanism is also different in a fundamental way. Solar CM. S are magnetically driven. The energy released is stored in the configuration of the magnetic field and released when that configuration reorganizes. Betelgeuse's magnetic field, while measurable, is relatively weak, far too weak by standard calculations to drive an ejection of this magnitude through magnetic reconnection. The driving mechanism in Betelgeuse was almost certainly convective. A particularly energetic rising column of plasma, a convective cell carrying far more thermal and kinetic energy than usual, broke through the photosphere and effectively punched material outward. The kinetic energy of a rapidly rising column of superheated plasma, accumulated over weeks of rise through the convective envelope, was sufficient to accelerate surface material past the local escape velocity and into the circumstellar environment. This is a plausible mechanism. It is coherent with the ultraviolet observations, with the asymmetric geometry of the dust cloud concentrated in the southern hemisphere of the star, and with the subsequent disruption of Betelgeuse's pulsation. But the details, why this particular cell carried so much energy, what primed the conditions, whether there is a resonance between the convective and pulsation timescales that occasionally produces these extreme events, remain genuinely contested in the literature. The name surface mass ejection is now in use. The mechanism behind the named thing is still being worked out. What the mass loss models were missing. Stars lose mass. This is understood and has been part of stellar evolution theory for decades. As a star evolves through the red supergiant phase, it sheds material continuously through stellar winds. These winds are driven by radiation pressure from the star's luminosity acting on dust grains and molecules in the outer atmosphere. The radiation pushes the grains outward, and the grains drag the surrounding gas along with them. For a red supergiant like Betelgeuse, these winds are slow relative to the winds of hot blue stars, on the order of 10 to 30 kilometers per second, but they carry significant mass over the timescales involved. Mass loss rates for red supergiants are measured through infrared excess emission, the thermal glow of warm circumstellar dust, and through spectroscopic signatures of outflowing gas. These measurements are averaged over time, and they feed into stellar evolution calculations that track how a star's mass changes across its lifetime. The models assume that mass loss is, if not perfectly smooth, at least gradual on evolutionary timescales. The amount of material Betelgeuse ejected in the single 2019 event is comparable, by rough estimates, to what steady wind models would predict the star shedding over several decades of continuous flow, concentrated into weeks rather than years. This has implications that cascade through the models. If red supergiants regularly produce surface mass ejections of this kind, events not captured in standard mass loss prescriptions because they are episodic rather than continuous, then the total mass shed over a supergiant's red giant lifetime is likely higher than the models assume and distributed differently in time. A star that arrives at core collapse, having lost more mass than expected, might behave differently during the explosion. It might produce a different remnant. The relationship between initial stellar mass and final remnant type, a relationship that underlies much of our understanding of how galaxies are enriched with heavy elements, rests partly on these mass loss histories. One event doesn't rewrite stellar evolution, but one event is evidence that an assumption hidden deep in the models, that episodic mass ejections of this magnitude don't occur or are rare enough to be negligible, may not be warranted. The question now is how common this behavior is, and the answer is not yet available. The stars we aren't watching. There are, in our galaxy, a small number of red supergiants close enough and bright enough to study in meaningful detail. Betelgeuse is the nearest. It is also by far the most intensively monitored, with a dedicated global community of observers, professional and amateur, and a continuous observational record stretching back over a century and a half. Beyond that small set, Betelgeuse, Antares, Phawai Canis Majoris, Mu Cephei, a handful of others, there are hundreds of red supergiants in the Milky Way. Most of them are visible only as faint points in moderate telescopes, resolved as individual stars, but not as objects with detailed surface data. They have spectral classifications, approximate masses estimated from their luminosity, rough distances from parallax surveys. What they don't have is a century of continuous photometric monitoring, no AAVSO for each of them. For most red supergiants in the Milky Way, we have intermittent photometry at best, a handful of measurements across years or decades, enough to confirm variability, sometimes enough to identify rough periodicities, not enough to detect a surface mass ejection of the kind Betelgeuse produced in 2019. Which, if it had occurred in an unmonitored star, would have been invisible to us unless we happened to be pointed at it at exactly the right time. This is the implication that sits uncomfortably. If Betelgeuse did this, and we detected it because we've been watching this particular star for over 150 years, then the question is, how many other red supergiants have done something similar in the past century? In the past decade, are doing it right now? The honest answer is that we don't know. The data to answer the question doesn't exist for most of the red supergiant population. The monitoring isn't there. Some of those unmonitored stars are in later evolutionary stages than Betelgeuse, closer to core collapse. Their pre-supernova mass loss history, the parameter that most directly shapes what kind of supernova they produce, may differ substantially from model predictions for the same reason Betelgeuse's does. When the next nearby supernova occurs, whenever that is, the question of what the progenitor star was doing in the years and decades before collapse will be scientifically critical. Whether the answer will be available depends entirely on whether that particular star happened to be in a monitoring program. We probably won't know. Tonight, that's where we'll leave it. The light arriving tonight is old. Betelgeuse is approximately 700 light-years from Earth. Light travels at roughly 300,000 kilometers per second. At that speed, it crosses the distance from the Sun to the Earth in about 8 minutes. It takes roughly 4 years to reach the nearest star. And it takes approximately 700 years to cross the distance between Betelgeuse and the planet you are lying on right now. The light arriving from Betelgeuse tonight left the star around 1325 CE. In 1325, the Mongol Empire was beginning to fragment following the death of Kublai Khan's successors. In Europe, the medieval warm period was giving way to what would become the Little Ice Age. The Black Death had not yet reached the continent. That would come in 1347. Dante Alighieri had been dead for 4 years. Ibn Battuta was in his early 20s at the beginning of his 30-year series of journeys. And on the surface of Betelgeuse, or rather in its outer convective layers, a massive bubble of plasma was rising, gaining energy, pushing upward. The particular convective event that would produce the dust cloud that dimmed the star, as seen from Earth, was underway. Nobody alive in 1325 knew this. Nobody knew what Betelgeuse was in the modern sense. There was no concept of a star as a distant sun. No one had measured its distance or inferred its mass. It was a bright reddish point in the winter sky above the figure of Orion, recognized by every culture in the northern hemisphere, and named variously in Arabic and Latin and Persian and languages that left no written record. The event that produced the Great Dimming happened 700 years before we observed it. By the time the light reached our detectors in October 2019, the dust cloud was already hundreds of astronomical units from the star and continuing to expand. The crisis, such as it was, had ended long ago. This is a quality of astronomical observation that never becomes entirely intuitive. The star we observe is not the star that exists now. Every measurement we take of Betelgeuse is archaeology, reading the light from an event that is already ancient from the star's perspective. The star as it exists in 2026 will not be observable until approximately the year 2726. Everything happening on its surface right now, whether it has produced another surface mass ejection, whether a new dust cloud is forming, whether the pulsation has done something unusual, is invisible to us. The information is in transit. What we know about Betelgeuse is the letter that arrived. There are letters still traveling. We won't read them in our lifetimes. After the dimming, the recovery. Betelgeuse reached its minimum measured brightness around late January to mid-February 2020, and then began to recover. By April and May of 2020, the star had returned to brightness levels more typical of its historical behavior. By summer, it had recovered to near its average. To a casual observer, the crisis seemed over. Orion's right shoulder was burning again. But the star was not unchanged. Beginning in late 2020 and extending into 2021, Betelgeuse entered a second notable dimming, less extreme than the Great Dimming, but statistically unusual. This event was substantially shorter and shallower than what had occurred in 2019 to 2020, and analysis suggested it was primarily driven by the star's pulsation rather than by another external dust cloud. But the pulsation itself was behaving differently. The 400-day oscillation, the cycle that had been semi-regular for the entire documented history of Betelgeuse observations, had been disrupted. The mass ejection of 2019 had removed a significant amount of material from the star's outer layers, specifically from the southern hemisphere. This asymmetric mass loss altered the internal pressure distribution and the convective dynamics that drive the pulsation. The oscillation, which had been building its current phase for decades, was effectively knocked off rhythm. Studies published in 2022 described this disruption in detail and proposed that the surface mass ejection had caused what they called a pulsation reset. The star's oscillation had been interrupted and was re-establishing itself with a new phase. Some analyses suggested the period itself had shifted, settling near 200 days rather than the traditional 400. Others argued that the 400-day cycle had simply been suppressed temporarily and would re-emerge. The debate about the post-dimming pulsation state is still active. It is, in a sense, a secondary scientific investigation opened by the main one, an inquiry into what the star's response to the ejection revealed about the relationship between convection, pulsation, and surface mass loss. By 2021 and into 2022, the pulsation had re-established some coherence. But the phase was different. The star's internal clock had been reset, or at least shifted, by a single convulsive event. The overbright phase and what it said. By the summer of 2023, something else had emerged in the monitoring data. Betelgeuse was unusually bright. Not slightly above average, measurably above its historical baseline in a way that was notable in the context of the full light curve. Some measurements from this period placed the star among the highest recorded brightness values in its documented history. This was the opposite of what had been observed just 3 years earlier. The overbright phase had been anticipated, in rough terms, by some theoretical models developed after the Great Dimming. The argument went like this. When the surface mass ejection removed material from the outer layers of the star, it transiently reduced the pressure confining the material below. The underlying layers, suddenly less constrained from above, expanded outward. Hotter interior material was brought closer to the radius at which we observe the photosphere. The effective luminosity increased as a result of this temporary expansion and heating. In terms of dynamics, the star had overshot its equilibrium state. The ejection had knocked it off the balance point around which it normally varies, and it was now oscillating above and below that point as it sought to restabilize. The 2020 to 2021 secondary dimming was one swing of this oscillation. The 2022 to 2023 overbright phase was another. By 2024 and 2025, the brightness was declining back toward historical averages. The oscillation was damping. Betelgeuse was returning toward its baseline. But baseline is a somewhat misleading term here. The internal structure of the star had been reorganized by the ejection. The convective flow patterns had changed. The pulsation phase had shifted. The outer layers had lost mass and reconfigured. The star settling back toward normal is settling toward a slightly different normal than the one that existed before October 2019. The overbright phase was a diagnostic, the way a struck bell reveals information about its internal properties through the way it rings. Betelgeuse revealed something about its internal dynamics through the shape of its response to the ejection. Researchers have used this response to constrain models of the star's interior. The depth of the convective zone, the structure of the pulsation-driving layers, the timescale of thermal relaxation. The match between the observed response and the theoretical models has been partial. The models capture the general trend. They don't fully match the timing or the magnitude. This is noted in the literature not as a failure, but as a boundary. Here is where the current models run out, and here is what remains to be improved. What lives beneath the photosphere? To understand why the surface mass ejection happened requires descending below the photosphere, below the layer from which we observe the light, into the interior that drives the surface. In Betelgeuse, at its current evolutionary stage, the core is not burning hydrogen. That phase ended millions of years ago. The core is now burning progressively heavier elements in a nested shell structure. Carbon in a central region, with helium burning in a shell above that, and hydrogen burning in an outer shell above that. Each layer produces energy at a different rate, with different waste products on a different timescale. The energy generated in these deep burning layers must be transported outward through the star to the surface, where it is eventually radiated into space. In the deep interior, radiation pressure handles much of this transport. But moving outward through the envelope, the vast outer volume that constitutes most of Betelgeuse's size, radiation becomes an inefficient carrier. The opacity of the material blocks the free flow of photons. Convection takes over. Hot, buoyant plasma rises. Cooler, denser plasma sinks back. This cycling of material carries thermal energy upward toward the surface, and it does so on a vast scale. The largest convective cells in Betelgeuse are thought to be something like a quarter of the stellar radius in diameter. Some models suggest even larger individual structures occupying a significant fraction of the star's volume. These cells rise over months, spend time near the surface over more months, and sink back down over years. Multiple such cells exist simultaneously, competing and interacting, sometimes merging, sometimes splitting. The energy budget of any individual convective cell is enormous. When a particularly energetic cell, one that has accumulated excess thermal energy during its ascent, or one that arrives at the surface simultaneously with a favorable phase of the star's pulsation, breaches the photosphere, it can launch surface material outward. This is the mechanical picture for the 2019 ejection. What made that particular cell unusually energetic? Whether it was a chance fluctuation, a resonance with the pulsation, an accumulation of energy from the deep burning layers, or some combination, is not fully known. The honest answer is, we're still working it out. The mechanism nobody agrees on. The great dimming was caused by dust. This is well established, with high confidence, based on the convergent evidence from ultraviolet, visible, and infrared observations. The dust was created from material ejected from Betelgeuse's outer layers. This is also well established. The ejection was most likely driven by a convective event, a particularly energetic convective cell breaking through the photosphere. This is the leading explanation, supported by the ultraviolet observations showing a pre-dimming brightening in the star's southern hemisphere. But here is what is genuinely unresolved: the details of the convective event itself. Why did the specific cell that produced the 2019 ejection carry so much more energy than typical convective cells? Was there a resonance between the cell's rise and the star's 400-day pulsation cycle, such that the pulsation and the convective upwelling reinforced each other at the surface? Was there a pressure accumulation below the photosphere that was released suddenly? Was there a role for the star's magnetic field, not as the primary energy source, but as a factor in concentrating or directing the ejection? None of these mechanisms are fully ruled in or ruled out. The observational data constrain the geometry and the timing, but don't directly reveal the driver. Theoretical models can be constructed that reproduce parts of the observed sequence under different assumptions about the underlying mechanism. No single model yet reproduces all of it. And then there is the deeper question. Is the 2019 ejection a rare occurrence in Betelgeuse's history, or a recurring one? The circumstellar environment around the star, the extended shells and asymmetric structures visible in infrared, shows complexity that is not easily explained by steady stellar wind alone. Some of this structure might be the accumulated record of previous ejection events, but this interpretation is uncertain. The same structures could arise from stellar wind variability, from pulsation-driven enhancement of mass loss, from the interaction of the wind with the interstellar medium. Whether 2019 was unprecedented or merely unusually well observed, that's a question the current data can't resolve. We still don't know. The red supergiants beyond Betelgeuse. Betelgeuse is not unique in being a red supergiant. It is unique in being the nearest one and by far the most closely monitored. The Milky Way contains somewhere in the range of a few hundred red supergiants, massive stars that have evolved off the main sequence and expanded into their current enormous, cool state. Most of these are scattered through the disk of the galaxy, many thousands of light years from Earth, visible only as faint resolved points in large aperture telescopes. Beyond the few named and studied individuals, this population is observed mostly through statistical surveys, infrared sky surveys that identify the characteristic colors and luminosities of red supergiants, photometric catalogs that document their positions and approximate brightnesses, spectroscopic campaigns that classify their spectral types and estimate their masses. What these surveys cannot provide, in most cases, is the kind of longitudinal monitoring record that would reveal a surface mass ejection if one occurred. The events happen on timescales of weeks to months. Detecting them requires dense, continuous observational coverage. This coverage exists for Betelgeuse and for a small number of other nearby bright red supergiants. It does not exist for the bulk of the galactic population. The Canis Majoris, one of the most luminous red supergiants in the Milky Way at roughly 5,000 light-years distance, shows a circumstellar environment of extraordinary complexity. Arcs, knots, and asymmetric structures extending outward from the star in multiple directions. The consensus interpretation of this structure involves a history of episodic directional mass ejections, events similar in character, if not identical in mechanism, to what Betelgeuse produced in 2019. The difference is that these events are inferred from the remnant structure, not observed in progress. The inference seems justified. The circumstellar geometry is not easily produced by smooth wind alone. But inference is not observation, and the details of when, how often, and through what mechanism these events occurred remain open. Antares, the other shoulder. Antares, Alpha Scorpii, is the red supergiant that shares the most physical resemblance to Betelgeuse among the stars visible from the northern hemisphere. It is slightly further, roughly 550 to 600 light-years away compared to Betelgeuse's 700. It occupies a similar region of the Hertzsprung-Russell diagram, a cool, luminous red supergiant with a mass probably between 11 and 14 solar masses. It pulsates. It has a measurable circumstellar envelope. It has been monitored as a variable star for over a century, though the monitoring record is less dense than Betelgeuse's because Antares is visible from northern latitudes for fewer months per year and has historically attracted somewhat less dedicated observational attention. Spectroscopic studies of Antares' circumstellar environment have revealed asymmetries. The distribution of gas and dust around the star is not uniform in all directions. Some of this asymmetry may reflect the underlying convective structures on the stellar surface, directing mass outflow preferentially in certain directions. Some may reflect the influence of Antares B, a hot blue companion star orbiting at a separation of several hundred astronomical units, which ionizes part of the circumstellar material and may influence the local outflow patterns. Antares has not produced a documented surface mass ejection analogous to Betelgeuse's 2019 event. This could mean it doesn't produce them. It could mean it hasn't produced one in the monitoring window. It could mean it has produced them, and we haven't detected them because the monitoring coverage wasn't dense enough. These three possibilities are not equally weighted by prior expectation, but they're also not trivially distinguishable from available data. Antares deserves more continuous monitoring than it currently receives. It is close, massive, and evolved. Any of the reasons that made Betelgeuse's 2019 event important apply with comparable force. The architecture of the surrounding void. At a distance of several stellar radii from Betelgeuse, several billion kilometers outward, the star is surrounded by material it has shed over its lifetime. This circumstellar envelope is not a smooth sphere. Infrared observations at different wavelengths reveal layered structure, an inner region of warm dust close to the star, a cooler outer region further away, and beyond that, arcs and asymmetric features that suggest the outflow has been directional and variable over time. The Herschel Space Observatory, observing at far infrared wavelengths invisible to ground-based telescopes, produced an extended image of the region around Betelgeuse, revealing a bow shock structure, a curved arc of material at the leading edge of the star's direction of motion through the local interstellar medium. As Betelgeuse moves through the sparse gas that fills the space between stars, the circumstellar material flowing outward from the star rams into the local interstellar gas and dust. This collision creates a compressed region, the bow shock, visible in far infrared as a faint but structured arc. The shape and size of the bow shock constrains the speed of the stellar wind and the density of the surrounding interstellar medium. It is, in effect, a bow wave, the same structure that forms in front of a boat moving through water, but on a scale of light years. All of this material, the shells, the arcs, the bow shock, represents the accumulated output of Betelgeuse over thousands of years of active mass loss. The dust cloud from the 2019 ejection is currently close to the star, within a few astronomical units, and expanding outward. It is a small and dense addition to this much larger and more diffuse structure. Over centuries, it will mix into the inner envelope. Over thousands of years, it will become indistinguishable from the steady wind material already present. But right now, it is there. A recently formed cloud made of material that was part of the photosphere of a star in 1319, moving outward into space at a few tens of kilometers per second, becoming part of the interstellar inventory, becoming part of the eventual raw material of whatever forms next in this region of the galaxy. Stars are not closed systems. They are continuously contributing to the medium around them. The spectroscopy of dust. The reddening observed during the Great Dimming was not just a matter of Betelgeuse looking visually redder. It was a quantitative shift in the spectral energy distribution, the amount of light at each wavelength, that could be measured precisely and compared against theoretical predictions. Dust reddening has a characteristic signature. It is not a simple dimming where all wavelengths are reduced by the same factor. It is a wavelength-dependent attenuation. Short wavelengths are reduced more than long ones, with the extinction following a power law across the optical and near-infrared range. This produces a distinctive reddening curve that has been studied in interstellar dust clouds for over a century. The reddening of Betelgeuse during the dimming followed a curve broadly consistent with dust extinction. More reddening than a pure temperature change of the photosphere would produce, and with a spectral shape that distinguishes it from simple surface cooling. Additional spectroscopic observations revealed signatures consistent with silicate dust grains, broad absorption features in the infrared at wavelengths characteristic of silicon-oxygen bond vibrations. These features are well known from studies of circumstellar dust around evolved stars and from interstellar dust clouds. Their presence in the spectrum of Betelgeuse during the dimming provided direct evidence for the presence of solid silicate grains, not just gas, along the line of sight. The inferred grain sizes from these observations were relatively large compared to the fine interstellar dust that accumulates in molecular clouds over millions of years. Large grains condense rapidly from cooling gas under conditions of high density, consistent with freshly ejected cooling stellar material rather than ancient interstellar dust. The spectroscopic fingerprint of the dimming was, in retrospect, diagnostic. Had the same level of analysis been available in real time, the dust explanation might have been established significantly faster. How dust forms from a star. The photosphere of Betelgeuse is at roughly 3,500 Kelvin. This is hot enough to keep most chemical species in atomic or simple molecular form. Silicon exists as individual atoms or possibly simple diatomic molecules in the stellar atmosphere. The conditions for solid grain formation, for silicon and oxygen atoms to combine with each other and with other elements to build crystalline lattice structures, do not exist at this temperature. When material is ejected from the photosphere and moves outward, two things happen simultaneously. The material expands, and it moves away from the star's heat. Both processes cause cooling. The density drops as the material expands into a larger volume. The temperature drops as the distance from the stellar heat source increases. The critical temperature for the condensation of silicate grains, the formation of solid particles from a gas of silicon, oxygen, magnesium, and iron, is approximately 1,500 Kelvin. Below this temperature, the thermal energy is no longer sufficient to break the chemical bonds that hold a grain together as fast as new atoms are landing on its surface. The grain nucleates and grows. In the material ejected by Betelgeuse in 2019, this temperature was reached within weeks to a few months of the initial ejection, depending on the velocity and initial density of the outflow. The grains that formed were silicate in composition, consistent with the spectroscopic observations. Silicate grains are highly effective at absorbing and scattering visible light. Their extinction cross-section is large relative to their physical size. A cloud of silicate dust with a relatively modest total mass, distributed over an area comparable to several times the stellar disk, can significantly reduce the apparent brightness of the star behind it when viewed from a particular direction. The geometry of the ejection was not symmetric. It was concentrated toward the southern hemisphere of Betelgeuse. This meant that the dust cloud, as seen from Earth, covered a substantial fraction of the visible disk. Not all of it, but enough to produce the observed dimming. Plasma became dust. In weeks, 700 years ago, and the light of that dust cloud, the darker pattern of absence it cast, arrived at our detectors in October 2019. A network built for exactly this moment. The 2019 to 2020 Great Dimming was characterized through a genuinely international, multi-instrument effort. Amateur astronomers contributing to AAVSO provided the densest photometric coverage, nightly measurements that tracked the dimming in near real time and provided the baseline comparison against the 150-year historical record. Without this community, the initial recognition that the dimming was anomalous would have been delayed and less certain. Ground-based professional observatories contributed visible light spectroscopy, tracking the Doppler velocities of material in the circumstellar environment, looking for evidence of outflowing gas, monitoring the spectral energy distribution across the optical range. Infrared observatories contributed thermal emission measurements, probing the dust at wavelengths where it emits rather than absorbs, providing constraints on the dust temperature, grain size, and total mass. The Hubble Space Telescope contributed the decisive ultraviolet observations, reaching wavelengths absorbed by Earth's atmosphere and therefore inaccessible from the ground. The ultraviolet data showed the pre-dimming convective outburst and the subsequent upper atmosphere brightening that preceded the optical decline. SOFIA, the Stratospheric Observatory for Infrared Astronomy, a large telescope mounted in a Boeing 747 aircraft flying above most of the atmospheric water vapor, contributed mid-infrared observations that bridged the wavelength gap between ground-based infrared and space-based ultraviolet, providing additional constraints on the dust properties. The eventual explanation was assembled not from any single observation, but from the convergence of all of these, each instrument covering a different wavelength range, a different spatial scale, a different physical property of the system. The confidence in the final picture is proportional to the number of independent measurements that point in the same direction. This is how science actually works at its best. Not a single genius moment of revelation, but a slow, distributed assembly of evidence from many sources, each contributing a piece until the shape of the answer becomes legible. The dust that will outlast the star. The dust cloud from the 2019 ejection is currently expanding outward from Betelgeuse at roughly 30 kilometers per second. A typical outflow velocity for material shed by a red supergiant. At that speed, over a human lifetime of roughly 80 years, the cloud would travel approximately 75 billion kilometers, about 500 times the distance from the Earth to the Sun, or roughly half the light travel distance to the nearest star. Over the lifetime of the star, the remaining 100,000 years or so before Betelgeuse goes supernova, the cloud will travel far enough to have fully merged into the broader circumstellar envelope and, at its outer edge, begun mixing into the surrounding interstellar medium. The dust will dilute, disperse, and eventually become part of the general interstellar inventory in this region of the Milky Way. Interstellar dust is not empty space. It is the accumulated output of billions of stars across galactic history, carbon grains from carbon-rich evolved stars, silicate grains from oxygen-rich red supergiants like Betelgeuse, ice-coated grains in cold, dense clouds, processed and reprocessed over the lifetime of the galaxy. When we see the Milky Way crossing the night sky as a faint band, part of what dims and reddens that light is this accumulated dust, the sedimented debris of stellar generations. When a new star forms, when a dense cloud of gas and dust collapses under its own gravity, eventually igniting nuclear fusion in its core, it collapses through this interstellar material. The dust, along with the gas, forms the rotating disk from which planets condense. The rocky, silicate-rich planets that form in the inner regions of such disks are built partly from this material, inherited from earlier generations of stars, processed through stellar interiors, shed into space, and redistributed across the galaxy over billions of years. The dust from the 2019 ejection will, in some infinitesimally small but real fraction, become part of the interstellar inventory. Billions of years from now, it might contribute to the disk around a newly forming star. It might end up incorporated into a rocky planet somewhere in the galaxy. Material from a red supergiant's outer layers scattered into space in 1319 CE might one day be part of the ground someone walks on. The star that keeps changing. Current monitoring of Betelgeuse, as of the mid-2020s, shows a star that is active and variable, but not acutely anomalous. The pulsation, disrupted by the 2019 ejection and its aftermath, has re-established coherence. Photometric data show the 400-day cycle operating within something like its historical range of variability, though with a phase that differs from what was observed before the Great Dimming. The longer multi-year cycle is also present. The overbright phase of 2022 to 2023 has declined. The star's brightness is trending back toward its historical average. This evolution is consistent with the rebound model, the initial overshooting of the equilibrium state following the ejection, the subsequent damping of that overshoot, and the gradual return to something like the pre-ejection baseline, modified by the internal reorganization that the ejection caused. No second surface mass ejection of comparable scale has been detected since 2019. There are reports of minor ultraviolet anomalies in 2022 that may indicate a smaller ejection event, but the evidence is ambiguous and the consensus interpretation favors normal variability over a true SME. The circumstellar environment continues to evolve. The 2019 dust cloud, now 6 or more years old and having traveled hundreds of astronomical units from the star, has thinned. Its optical depth, its capacity to block light from reaching Earth, has decreased to the point where it no longer measurably affects the star's apparent brightness. It is still there, moving outward. But from Earth's perspective, it is transparent. Betelgeuse, in the current view, has returned to something resembling its pre-dimming behavior. Not quite the same star. The pulsation phase has shifted, the internal structure has reorganized, but close enough that routine monitoring can continue without elevated alert. The community is still watching, more closely than before. The clock we cannot read. Betelgeuse will go supernova. This is the certain part. The uncertain part, the part that every researcher who studies this star eventually has to sit with and then set aside, is the timing. Estimates for the time remaining before core collapse span a range that makes the uncertainty explicit, from a few thousand years to possibly over 100,000 years. This is not a case where the models are sloppy or the data is sparse. It is a fundamental limitation, the parameter that most directly determines the remaining time, the current state of the deep core, the mass of the iron-nickel center, the rate of energy generation in the overlying burning shells is not directly observable. The core is hidden by hundreds of millions of kilometers of overlying stellar material. Neutrinos produced in the core escape freely, but the flux reaching Earth is below current detection thresholds in the pre-collapse phase. We infer the core's likely state from surface properties, the luminosity, the temperature, the pulsation. These constrain models, and the models give probability distributions over the remaining lifetime. But these are probability distributions, not predictions. They span orders of magnitude. The surface mass ejection of 2019 has added a subtlety to this already uncertain picture. The ejection removed mass from the outer layers. Stars in more advanced evolutionary stages, with higher mass cores, tend to have higher pulsation luminosities and faster evolution. A star that has lost more mass than expected, however, has a slightly lower external pressure on the core, which can modestly slow the evolution of the core itself. This counterintuitive effect, a violent surface eruption that might slightly delay rather than accelerate the time to core collapse, was noted in the literature after 2022. The magnitude of the effect on the timing estimate is probably small. But it is one more reason that the timing uncertainty, already large, is not getting smaller. We live in the shadow of a question we cannot answer. The star will explode, we don't know when. We'll know when it happens, because the neutrino burst will arrive first, and the detectors will fire, and alerts will propagate through the astronomical community in minutes. Until then, we wait and watch. What the core is doing. We cannot see the core of Betelgeuse directly. No wavelength of light can reach us from there. The overlying material is opaque. The interior is known only through inference, through stellar evolution models calibrated on populations of stars, and through the surface properties of this particular star. But the models tell a coherent story. A star of Betelgeuse's mass at the red supergiant phase has already exhausted hydrogen and helium in its central regions. The core is most likely burning carbon, fusing carbon nuclei into oxygen, neon, and magnesium, releasing energy in the process. Above this carbon-burning core, a helium-burning shell generates additional energy. Above that, a hydrogen-burning shell. The star's energy production is distributed across these concentric zones, each operating on progressively shorter timescales as the reactions proceed. Carbon burning in the core of a massive star lasts on the order of 1,000 years. For Betelgeuse, carbon burning is ongoing, or neon burning has already begun. Models place this stage in the uncertainty range for Betelgeuse's current evolution. Neon burning lasts roughly a year. Oxygen burning, the next stage, takes months. Silicon burning, the final fusion stage before iron, takes days to weeks. After silicon burning produces an iron core of sufficient mass, no energy can be extracted from further fusion. Iron is the most tightly bound nucleus in nature. Adding to it or splitting it requires energy rather than releasing it. When the iron core exceeds roughly 1.4 solar masses, electron degeneracy pressure, the quantum mechanical resistance of electrons to being compressed, can no longer support it against gravity. The core collapses in less than a second. This is the event that produces the neutrino burst, the shock wave, the supernova. From outside, the star will not look different in the moments before collapse. There is no visible warning. The surface is blind to what is happening in the core thousands of kilometers below. The light from the final moments of the star's life, Whatever happens on the surface as the shock wave begins its journey outward will not reach Earth for 700 years. The network waiting for the signal. After SN 1987, demonstrated that neutrinos from stellar core collapse could be detected on Earth, the case for a dedicated early warning network became compelling. The idea was straightforward. Build sufficiently sensitive neutrino detectors at multiple independent sites around the world, connect them to a shared alert system, and establish an automated protocol for cross-checking signals. If two or more detectors simultaneously record a burst of events consistent with a nearby core collapse supernova, trigger an alert to optical and radio observatories so they can begin recording before the visible light peaks. This is SNEWS, the Supernova Early Warning System, operational since the late 1990s, updated through several iterations, now encompassing detectors in Japan, the United States, Canada, Italy, and Antarctica. The flagship detector for this network is Super Kamiokande in Japan, a 50,000-ton tank of ultra-pure water, observed by nearly 13,000 photomultiplier tubes embedded in the walls of an underground chamber deep in a mountain. The tank is sensitive to the faint flashes of light, Cherenkov radiation, produced when neutrinos interact with water molecules. For SN 1987A, the predecessor Kamiokande detector captured roughly 11 events from the neutrino burst. Super Kamiokande, far larger, would capture tens of thousands of events from a Betelgeuse distant supernova. IceCube, buried deep in the Antarctic ice at the South Pole, would register a diffuse increase in count rate across its entire array, not from individual neutrino interactions resolved separately, but from the collective statistical signal of thousands of interactions across a cubic kilometer of instrumented ice. The alert from SNEWS would propagate to registered observatories within seconds of detection. Those observatories, including space telescopes capable of capturing ultraviolet and X-ray emission within the first hours, would point toward Betelgeuse before the visible light peak. The rise of the optical light curve, captured from its very beginning, would be one of the most scientifically rich datasets in the history of observational astronomy. The network is ready, the telescopes are ready, the protocols are in place. The star is operating on its own schedule. What gets left behind? The question of what Betelgeuse leaves after core collapse, what remnant sits at the center of the expanding debris cloud, depends on the mass of the core at the moment of collapse and on the details of the explosion itself. If the iron core that forms is between roughly 1.4 and approximately 3 solar masses, the collapse produces a neutron star. Neutrons, unlike electrons, can be compressed much further before quantum mechanical pressure halts the collapse. A neutron star roughly 20 kilometers across, the size of a city, contains roughly the mass of the Sun. Its density is comparable to atomic nuclear density. Protons and neutrons packed as tightly as they exist within a nucleus, with almost no space between. Neutron stars cool over millions of years, emitting thermal radiation that gradually shifts to lower and lower energies. Some rotate rapidly and emit beams of radio waves. These are pulsars, detected as precisely timed pulses as the beam sweeps past Earth. Some have intense magnetic fields far exceeding anything achievable in the laboratory, magnetars. Eventually, all of them cool to invisibility, becoming cold stellar remnants that drift through the galaxy for billions of years. If the core mass at collapse exceeds the maximum mass that can be supported by neutron degeneracy pressure, roughly 2 to 3 solar masses, with the exact value uncertain, then the collapse continues past neutron star density. A black hole forms. Nothing further can be said about what happens inside it from an outside observer's perspective. Information from below the event horizon is permanently inaccessible. For Betelgeuse, current estimates favor a neutron star remnant. The initial mass, the mass loss history, and the resulting core mass at collapse are all within a range that most models place below the neutron star to black hole threshold. But most models is not all models, and the uncertainty in the mass loss history, now explicitly enlarged by the 2019 ejection, means this conclusion is held with moderate rather than high confidence. There is also a third outcome, a failed supernova. In this scenario, the core collapses, but the shock wave it drives into the outer layers fails to propagate successfully. The outer layers fall back inward rather than being ejected. The star doesn't explode in the traditional sense. It simply vanishes, with a brief transient that is far dimmer than a typical supernova, leaving a black hole behind. Searches for this phenomenon in nearby galaxies have identified several candidates, stars that disappeared from survey images without a corresponding supernova detection. Whether Betelgeuse could produce a failed supernova is not known. It is a low probability outcome given current models. It is not a zero probability outcome. The winter constellation after. Orion is not a physical object. It is a projection. The stars that form the pattern are at vastly different distances. Betelgeuse at about 700 light-years, Rigel at roughly 860 light-years, the belt stars at 1,200 to 1,500 light-years. These are not neighbors. They are not part of any gravitationally bound system. They happen to appear in the same region of the sky, from Earth's perspective, in a configuration that humans found meaningful enough to name. The figure was already understood in different forms by cultures across the Northern Hemisphere before written records exist. The same 7 or 8 bright stars, recognized as a cluster, a figure, a hunter, a giant, appear in Babylonian astronomy, in ancient Egyptian star lore, in Greek myth, in indigenous astronomical traditions across several continents. The pattern is robust enough that independent cultures consistently found it recognizable. When Betelgeuse goes supernova, the constellation as a visual pattern loses one of its brightest members. But it doesn't lose it immediately and permanently. For months, the right shoulder blazes, brighter than everything else in the sky except the sun and moon. Then it fades. Over years, the position fades to naked eye invisibility. Over decades, to binocular visibility, then telescopic. Eventually, the expanding nebula is detectable only with large instruments. The gap it leaves is subtle. Orion has 8 or so prominent stars, and Betelgeuse is the brightest red one. Without it, the upper left corner of the pattern is empty. The figure becomes asymmetric in a new way. The shoulders unbalanced, one bright and blue-white, the other absent. This is what happens at the scale of the pattern. At the scale of the person standing under the winter sky, whether that person is 10,000 years from now or 10,000 years in the future, the change is simple. One familiar light is gone. The shape that has been recognized across every language and culture that developed in the Northern Hemisphere is slightly different now. It will take a few generations for the new version of Orion to feel as natural as the current one. The question that changes every star. The great dimming of Betelgeuse changed more than the understanding of one star. Before 2019, the dominant picture of mass loss in red supergiants was built on continuous processes. Stellar winds, steady, variable with the pulsation, somewhat enhanced during periods of high luminosity, were understood as the primary channel through which these stars shed mass over time. Episodic events were acknowledged as possible, but were not built into the standard prescriptions at the scale demonstrated by the 2019 ejection. After 2019, the picture must include at least one documented massive episodic event. The question, how does Betelgeuse lose mass? now has an answer with two components instead of one. And the second component, the surface mass ejection, moved more mass in weeks than the first component moves in decades. This revision has implications that propagate through astrophysics in ways that are still being traced. The mass a star retains when it undergoes core collapse determines the kind of supernova it produces, the properties of the remnant, and the amount and composition of material expelled into the interstellar medium. These quantities feed into galactic chemical evolution models, the models that track how the abundances of elements change over the lifetime of a galaxy as successive generations of stars form, live, shed mass, and die. If episodic surface mass ejections are a common feature of red supergiant evolution, rather than a rare anomaly of Betelgeuse, the mass loss histories assumed in these models are systematically underestimated, at least in their episodic component. The correction would be small on a per-galaxy basis. The contribution of individual stars is always small, but it represents a real bias in the input assumptions of many calculations. One event doesn't rewrite stellar evolution, but one event revealed that something had been left out of the theory, and the thing that had been left out was not small. What Betelgeuse gave us. It gave us a question we didn't know to ask. Not the questions that had been prepared. Is this the supernova precursor? Is this a star spot? Is this something familiar in an unusual form? It forced the creation of a new category, surface mass ejection, a name for a behavior that hadn't been formally recognized, because nothing had been close enough, bright enough, and well monitored enough to reveal it before. In the long history of astronomy, there are moments when a specific observation or event compels a revision not just of one theory, but of a framework of assumptions so embedded that they had become invisible as assumptions. The discovery that a nearby red supergiant could eject multiple Jupiter masses of material in a single convulsive surface event was such a moment, smaller in scope than the revision that followed the discovery of dark matter or the detection of accelerating cosmic expansion, but real in the same category of forcing a reconceptualization rather than a correction. The reconceptualization is still in progress. New papers continue to be published. New data from continued monitoring of Betelgeuse, from infrared surveys of other red supergiants, from theoretical models that now try to incorporate episodic mass loss alongside steady wind, are slowly reshaping the picture. There is a more prosaic thing Betelgeuse gave us, harder to quantify but also real: the attention of people who hadn't paid attention before. The winter of 2019 produced something unusual, a widespread public awareness that a specific star existed and was doing something interesting. Not all of that attention was accurate or well-informed. Some of the supernova speculation was premature and exaggerated. But some fraction of the people who looked up at Orion in February 2020 and noticed the dimmed right shoulder came away from that winter with something they didn't have before: the knowledge that stars are not static, that the sky changes, that something that appeared permanent is in fact always moving. That is not nothing. It is, in fact, the beginning of every serious relationship with the sky. 700 years of light and one winter. In October 2019, light that had left Betelgeuse in approximately 1319 CE arrived at Earth in a pattern that was different from any pattern that had arrived in the previous 150 years of careful measurement, and possibly different from any pattern that had arrived in the previous 1,500 years of human observation of the star. It arrived at photomultiplier tubes in automated survey telescopes. It arrived at charge-coupled devices mounted at professional observatories. It arrived at the eyes of amateur astronomers in New Mexico and Australia and Japan and Finland, who happened to be monitoring variable stars on cold, clear nights in November and December 2019. The dimming was real. The dust was real. The ejection that caused it had happened 700 years earlier, at a star that had no human beings thinking about it in any modern sense of that phrase. Because in 1319, the concept of what Betelgeuse was, physically, didn't exist. What changed between 1319 and 2019 is not the star. The star is indifferent to being observed. It doesn't know we watch it. It doesn't know we've named it, mistranslated the name, argued about the mistranslation, and settled on the corrupted version. It doesn't know we built spectrographs and photometers and placed a telescope in orbit and pointed that telescope at its southern hemisphere to catch the ultraviolet signal of a convective eruption that had already occurred before that telescope was launched. What changed is that we became capable of reading the light. Not just registering it. Animals have been doing that for hundreds of millions of years. Reading it, extracting from the precise wavelength distribution, the temporal variation, the multi-wavelength morphology, a description of physical events happening at a star 700 light-years away. For 6 months in 2019 and 2020, a single star, one we had been watching carefully for over 150 years, casually for much longer, used our instruments to tell us something about itself we hadn't known. Something it had apparently been doing, possibly for its entire red supergiant life. Without an audience. We've drifted through a long story tonight. Through the winter, when Orion's shoulder dimmed and the world noticed. Through the convective bubble that broke through a stellar photosphere 700 light-years away, in a year when nobody alive today had yet been born. Through the cooling plasma and the condensing silicate grains and the dust cloud that traveled 700 years to cast its shadow across our instruments. We've sat with the scientists who assembled the answer, not in a single moment, but through months of converging evidence from amateur photometrists, from space telescopes, from infrared observatories and ultraviolet campaigns and spectroscopic surveys, each instrument seeing a different piece of the same event. We've touched the question of what happens when Betelgeuse finally does what gravity has been preparing it for across its entire life. The neutrino burst arriving hours before the light, the optical fireball rising over days, the slow dimming over years and decades, the gap it will leave in the shape of Orion. And we've carried the unresolved piece, the hundreds of red supergiants we are not watching, doing things we cannot know, in parts of the galaxy where no monitoring program has reached. What the dimming gave us in the end was not certainty. It gave us a better map of where the uncertainty lives, a more precisely located gap in what we understand about how stars age and shed mass and prepare to die. That kind of correction, not an answer but a sharper question, is how the picture of the universe improves slowly across generations of observation and revision. Betelgeuse is still there. Still burning orange-red in the winter sky, still pulsating on its long irregular cycles, still surrounded by the shells and arcs of material it has shed across millions of years. And the light arriving from it tonight left the star around 1325, traveling toward you since before the printing press, before the compass in European hands, before the age of telescopes, arriving now at your sky at this particular winter. If your eyes feel heavy, let them close. If this felt like home, leave a comment when you wake up. If you're still here, the next chapter is waiting. The universe will still be here when you wake up. So will we. Good night.